Greetings, gang, and welcome to your Chapter 24 lecture video on electricity and magnetism. By now we've had a decent amount of experience with electricity. However, there is a very closely related phenomenon that is completely and utterly indivorceable from electricity, and that, of course, is magnetism. But what is magnetism, and where does it come from? We've all played with fridge magnets, so we probably understand that the single simple principle seems to govern their behavior, and that is, very much like electric charges, like poles repel each other, but opposite poles attract. And if you take two magnets and you stick them together a certain way, they repel each other, but if you stick them together a different way, they stick together, right? Not terribly unlike electricity. So what happens if you bring two magnetic poles close to each other? Well, they could possibly attract each other or repel each other, right? Now, let's say that you have two magnetic poles aligned such that they are going to attract towards each other. If they get pulled farther away, does that force increase or decrease? What happens to the strength of the magnetic attraction if instead of two weak magnets, you have two really, really strong magnets when they get close to each other? Well, that means a couple of things, right? That the strength of the magnetic force depends on the strength of the magnetic poles themselves, and also upon how far apart they are. Notice we've also got this 4 pi r squared, that's the surface of a sphere again, right? And so we can automatically assume that the sphere of influence, the magnetic field of a magnet, radiates out into the universe spherically, all things being equal. That means also we could take this 1 over 4 pi mu naught, which is the vacuum permeability, or how easily it is that a magnetic field can permeate through the vacuum of space. We could technically just take all of this and absorb it into another constant, and it would look just like Coulomb's law, or the law of universal gravitation, right? Some number times 1 over r squared times the magnitude of two poles in this case, instead of two masses or two electric charges. So this is an inverse square law. If things get separated by a certain distance, they have a certain strength. Doubling that distance makes it decrease by a factor of 4. Having the distance makes it increase by a factor of 4, just like all of our other inverse square laws. Now, just like how the region of space around a charge is permeated by an electric field, the region of space around a magnet is permeated by a magnetic field. Magnetic fields are said to be drawn or represented in a way that's not terribly dissimilar from charges. We said before that electric field lines start on a positive charge and end on a negative charge. Here we usually say that magnetic field lines, we don't usually have a positive and negative. We say a north pole and a south pole, right? And magnetic field lines are said to start on north poles and end on south poles. So here it would loop this way, here it would loop this way, right? So what does a magnetic field actually look like then? Well, I want to show you. Here I've got a bar magnet. And here, in this jar, this is an old Frappuccino bottle that I've tried to take all the labeling or whatever off of. In the bottom, there's some iron filings, and I've super glued like a little slot to drop the magnet in. And what I'm going to do is I'm going to shake this up. It needs a little bit of encouragement. I haven't used this in a little while. There we go. Now we've got a bunch of iron filings all over this. This liquid, by the way, is magnetically neutral. It has no magnetic moment. It's mineral oil, like baby oil. Now if I drop this magnet in here, and we just kind of let it sit for a second, and let a bunch of the iron filings just kind of fall away. You should begin to see the shape of the magnetic field here. It becomes really obvious against a white background, right? That's the actual shape of the magnetic field. Those lines, those spines of iron filings are essentially exactly these magnetic field lines. And if you don't believe me, watch what happens when I take the magnet out. Nothing, right? And so really what we're looking at here is a 3D map of the magnetic field, right, in 3 dimensions. But where does magnetism come from? Why is it so closely related to electricity? Long story short, electric fields can be generated by changing magnetic fields, and magnetic fields can be generated by changing electric fields. The two phenomena are actually part of one larger phenomenon, one greater phenomenon that we know as electromagnetism, right? Electricity and magnetism are indivisible, they are inextricably married, and they can never be separated. Suffice to say, that it has been known for a very long time, mathematically and scientifically proven, all that, but the reasons mostly require math that we don't want to use, as relativity and quantum mechanics are sort of out of sight of the scope and bounds of this course. I'm trying to get it close enough that we can really get a good, clear view of what this magnetic field looks like. In any case, we're not going to get too much into the nitty-gritty math of quantum mechanics or relativity, but suffice to say, a charge moving means the space around it is going to see a change in the electric field in that region of space, right? If a charge is moving away from you, it's going to look like there's less of an electric field in the space in between you and it as it's moving away, right? The electric field is going to appear to be getting weaker in that region of space. Moving charges means a magnetic field. For most common magnets, the moving charges are the electrons in the metal itself. There's a phenomenon that we call spin-orbit coupling. If you remember, let's say we take the hydrogen atom, for example, right? Hydrogen atom has one proton here and one electron here. Now this electron can either be spin up or spin down. And as it orbits around, there is going to be a little bit of angular momentum both from the orbit and from the way that the electron is spinning. Now, the electron can spin in a way that's complementary to its orbit or against its orbit. And so this slight variation, right, the addition of these momenta and the changing of the electric field in the space around this atom is enough to explain the magnetic force in this region of space. Let's say we're dealing with a small piece of iron, like the filings from our friend, the magnetic field bottle. Even a small piece of iron has, tons of electrons in it. And if all of those electrons are kind of moving in the same direction, right? They're all spin-orbit coupling kind of in the same direction, then the magnetic field generated by all of these electrons should align together, right? And so if the region of these aligned electrons is really small, then it's only going to generate a small amount of magnetic field in the same direction. But if it's larger, so let's say we've got, an iron bar, and we've got one tiny little what we call a magnetic domain, where a bunch of the electrons are all kind of spin-orbit coupling together. That means there's going to be a little bit of a magnetic field as a result of this. But if that region is larger, there's going to be more of a magnetic field, right? As a result. Now, most of the time, if you just grab a chunk of iron that occurs in nature, the domains are going to be very small and kind of randomly oriented all over the place. However, if you take a really strong magnet and you stick it next to this piece of iron, all the magnetic domains can align and make the iron into a permanent magnet. I got a little bit of the mineral oil on my hands, so if you'll excuse me for a second, I gotta wash it off. Just like a real lecture, right? You gotta wait for Mr. Kemp to go and wash his hands so we can keep going. In any case, this is actually how your microwave oven works. There's a very strong magnetic apparatus called a magnetron inside the microwave that is able to turn on a really strong magnetic field in one direction and then turn it on in the other direction. Now, what is that going to do? So let's say this board is now your microwave chamber, right? And you turn on a really strong magnetic field this way, right? And so that's going to make all of the water molecules in your food align a certain way. Why? Well, the water molecule kind of looks like this, right? Kind of like Mickey Mouse. These are the hydrogen atoms. This is the oxygen atom, and this makes your water molecule. Now the hydrogens are slightly positive, and the oxygen is slightly negative, and that makes water just slightly polar, right? So it's a slightly polar molecule, and so this strong magnetic field can cause the water molecules to align. And so if this is our alignment axis, it can like align with the magnetic field this way, right? It'll turn the water molecules. Now the magnetron will turn on this way, and then it'll turn off, and then it'll turn on the magnetic field this way and make the water molecules reorient themselves the other way. What is that going to do? Well, the water molecules are going to turn this way and that way, this way, that way, this, right? And the stronger the power in the microwave, the more quickly it's changing its magnetic field, right? Whatever cooking power you set it to. Now what that does is it causes these water molecules to rub up against, vibrate the other molecules in the food that it's in contact with. That causes friction and therefore heat. And that is why your microwave oven is able to cook your food. And it really makes a lot of sense if you think of moving charges in magnets as currents, right? Now, since a current is a changing electric field, right, you're talking about a moving charge, it generates a magnetic field. And it is for this reason that a current-carrying wire generates a magnetic field. We call this an electromagnet, or a magnet that's only a magnet when there's an electric current running through it. Electromagnets are actually really useful, and that's a great example of how this maglev, or magnetic levitation technology, is sort of on the rise. I've included a link to a quantum locking video. This is a video that was made to showcase what happens when you take a superconducting magnet. And if you remember, a superconductor is something that can conduct electricity with zero loss of energy. Right? You take a superconducting magnet, generally something that's at a very, very low temperature, right? Now, when you have a superconducting magnet, its quantum states, its magnetic states lock into place. And the consequences are really quite spectacular. So this is a good time to pause and watch the quantum locking video. Now, imagine an entire train on these maglev rails. Obviously, a train can only do what the quantum lock magnets did if the magnet itself, the maglev rails, are superconductors, right? Which is why we've got a long ways to go before we're going to have reliable, room temperature superconducting magnets and maglev trains that aren't going to cost lots and lots of energy. In any case, most of our superconducting magnets are in MRI machines because they're so sensitive that we can actually see the brain activity of somebody who's inside one of them. Or at scientific installations like the Large Hadron Collider, the LHC in Switzerland. That's where most of our superconducting magnets are. But I digress. We know that magnetic fields can exert a force on charges, but how does that work exactly? Well, a magnetic field can only exert a force on a moving charge. Because recall that a moving charge can generate a magnetic field. How exactly do these things interact? Well, they interact based on this funny thing called the right-hand rule. Now, let's say, for example, there's a magnetic field going into the board here, okay? So let's say our B field, our magnetic field, is going into the board in this region. And we use our right hand to try to figure out the direction of this thing, the way that this works, okay? So let's say we've got a positive charge, and it goes this way. Now there's going to be a force that this magnetic field is going to assert on this charge here, Q. What direction is that force going to be, and what is that going to do to the charge? Well, so the magnetic field is this way. The positive charge is moving this way. And so if we put the direction of our index finger along the velocity, or the direction that the charge is moving, and we put our middle finger along the direction of the magnetic field, right, such that they're sort of mutually perpendicular to the direction our thumb sticks out, the direction of our thumb is going to tell us the direction of the magnetic force, right? So here, the force is going to be this way. Now this only works if you use your right hand. If you use your left hand, it'll tell you the wrong direction, right? Which is why they call it the right-hand rule. So we've got a velocity this way, we've got a magnetic field this way, our thumb is going to tell us the direction of the force. And so what's that going to do? Well, we got it moving this way, it's going to feel a force perpendicular to the way it's going. That's going to make it turn, right? And then as it turns, it's going to keep making it turn. And so this is going to make it follow a circular arc, as long as it's still inside this magnetic field. Now the Earth is known to have a magnetic field. We all know that we can use a compass to find where north is, but there is a difference between what we call true north, or axial north, or where what we call the North Pole is, and magnetic north. In fact, the magnetic poles of the Earth move over the course of time. In a few hundred years, what we call the magnetic North Pole, which is actually a south magnetic pole, right? And if you don't believe me, you have a magnet in your compass and the north end of that magnet is pointing towards the north, the magnetic North Pole. And remember, North Poles are attracted to South Poles. Anyway, like I said, the magnetic poles of the Earth change over the course of time, and in a few hundred years, what we call the magnetic North Pole, which is actually a South Pole, is probably going to be in Siberia. But why is that? Well, magnetic fields, of course, are always the result of moving charges or changing electric fields, like always. This time, it's the motion of all of the molten rocks and lava, metals, things like that, below the surface of the Earth. So in the very center of the Earth, we have like a solid core. And then there's a bunch of this molten stuff, right? And then there's this place we call the lithosphere, which is this kind of thin layer on the surface that the world that we know rests on. Now, because there's a bunch of heat being released here, there are these things we call convection currents, right? And over the course of time, the direction of these convection currents can change a little bit. And if the overall motion together kind of moves things in a certain way, then we'll have a magnetic field that looks like this. And right now, that's kind of what we got, right? This is our magnetic north, even though the North Pole is actually here, the South Pole is actually here. We've got a south magnetic pole and a south actual axial pole that are slightly different, right? Just like we've got a north magnetic pole and a true North Pole that are slightly different. And in any case, they're going to change a little bit as these convection currents of this charged material below the surface of the Earth continues to change. Now, the Earth's magnetic field has been known to reverse itself every couple 100,000 years or so. Not terribly unlike how the Sun has a repeating 22-year pattern of sunspots. And I really want to show you a picture of this one if I can find it here. So here we have an image of the location of sunspots on the surface of the Sun. If you look over here, we've got this middle line representing the equator of the Sun. Okay? This is 30 degree north latitude, 30 degrees south latitude, and these are the poles. Now, you'll notice that it makes kind of a repeating pattern, and it's probably easy to see why we call it the butterfly pattern, right? Now, the reason that it looks like this is the Sun rotates, but it rotates differentially, meaning it rotates faster at its equator than it does at its poles. And the Sun is awash in magnetic activity. It's just got tons and tons of magnetism. It's so strong that we can detect it in the light even all the way from here. And because there's all this crazy magnetism. Why don't I show you a picture of this too? There's like solar flares and prominences. These things. These really interesting things, right? Now you'll notice that a solar prominence makes a loop. This is very clear evidence of magnetism, right? And that's why there are solar flares and all this other stuff. Those are actual sunspot activity phenomena, right? Now, you'll notice that at the beginning of one of these butterflies, the solar activity is nearer the poles, right? And it seems to narrow and narrow and narrow and narrow closer to the equator. And that happens as the sun continues to rotate faster at the equator. The magnetic bands on the surface of the sun wrap up tighter and tighter and tighter until most of the solar magnetic activity, a lot of it where these solar flares, these prominences, these sunspots are, happen closer and closer to the equator until finally the magnetic bands, the magnetic activity on the surface of the sun, are wrapped up so tight that it snaps and the poles reverse and it starts again. Now, unlike here on the Earth, where it takes a couple 100,000 years for the magnetic poles to reverse, it happens on the sun once every 11 years. And actually, you'll have a north pole on the top, and then it'll break and snap and it'll switch. And so it's actually two butterflies for a complete, what we call butterfly cycle, right? A complete solar cycle. In any case, that's what we call a butterfly diagram. Sometimes the magnetic surface of the sun and these sunspot phenomena, solar flares, prominences, and sometimes a coronal mass ejection, which can actually shoot material out from the surface of the sun, which are going to be hot and charged. Sometimes these hot charged particles make it all the way to the Earth from the sun. So I'm going to draw the Earth here. Here's our magnetic field, right? Now sometimes this stuff will make it all the way to the atmosphere and just kind of bounce harmlessly off. Sometimes this hot charged material can arrive here on the Earth somewhere near one of the poles where the magnetic fields are really, really strong. And if it does that, sometimes one of these particles can kind of wrap itself around the magnetic field lines, right, according to the right-hand rule, just kind of spiral around it. And that can give off a really interesting phenomena that we call the northern lights, or the southern lights, obviously, if you're in the southern hemisphere, right? The aurora borealis or the aurora australis. In any case, that's it for chapter 22. I hope you've enjoyed your lecture. I'll see you for chapter 25.